Our last keynote speaker in the morning session is Dr. Xian-Sheng. Dr. Xian-Sheng is now a distinguished engineer and vice president of Alibaba DAMO Academy, leading the visual computing team. Dr. Hua is an IEEE fellow, ACM distinguished scientist, and MIT TR35 Young Innovator Award recipient. He has authored or co-authored more than 200 research papers and has filed more than 90 patents. Dr. Hua will speak about the city brain.
Thanks. My name is Xian-Sheng from Alibaba, the biggest e-commerce company in China, also the biggest cloud computing company in China as well. And now it's more based on technology, data, and AI. So the topic I'm going to talk about is the recent big project that has been working on for 2 years, that is City Brain. So as we know, artificial intelligence has 3 golden times in the history. The first 2 golden times turned out to be only dreams, right? And now is the 3rd time. Is it a dream? Will be a dream again, or there will be any differences? Actually, there are many differences, including 4 things here. First, we have deep learnings that we have made big progress in many areas, and we also have huge computing capacities compared with a few years ago. And it's much easier for us to acquire massive amount of data. And the last but not the least, we have seen many successful applications such as search engines. There are a lot of AI technology behind, and also AlphaGo, and also online shopping recommendations. Sometimes the recommendation system know you better than yourself and your partners what you want to next, right? And face verifications and many more. So this shows that we have made considerable progress in AI technologies and applications. This also enables us to think about whether we can do something big to create a brain for a city, right? And we'll come back to this slide later to see what city brain will bring back to AI technology later. So from 10,000 feet in the sky, what is city brain looks like? Firstly, city is an aggregate of a huge amount of heterogeneous data, especially for video data. You know, in China, I'm not very sure in Israel, but in China, in the first-tier city, there are tens of thousands or even hundreds of thousands of cameras watching the city 24/7. This it generates a huge amount of data, but right now it's mostly used for catching traffic violations, and so you can get a considerable number of fines without too much effort. But we have put pounds of money to set up the cameras, to connect the cameras to a data center, stream the videos to the data center, tons of money. So what else you can do with those data? So this is the core of city brain. We want to use the fastly evolving AI technologies and the huge computation power to extract irreplaceable values from those data. We started this project 2 years ago. At that time, it was something like Mission Impossible because you want to process a huge number of videos. And there are 3 challenges. All the challenges from external and internal can be summarized into 3 keywords. First, cost. The cost will be very high, whether the cost will be manageable. Second is values. What kind of values we can get from those data? Is it worth the cost we are going to put on it? Third, even more challenges. More challenging is that is there any differences compared with the old terms, old concept, smart city, video surveillance, and the new, but actually not very new, edge computing. So I hope after this short presentation, you will have a better idea what the difference is here. So let's get closer to see what city brain looks like from 100 feet. First, we have a bunch of data types, especially for video data. Other data maybe can be used directly, but for video data, there are pixels, right? So we have to do something on that. The first step is called cognition or perception. That is, you want to analyze what's going on the road. the cars, the pedestrians, event, and many things. All the things that are happening on the road, we want to know. Based on that, we can do optimizations or decision makings. For example, accident alerting instantly or traffic light optimization. And then we can put all the visual objects that we detect from the road, from the street, into an index. So we can search anything you want. For example, if there's a hit and run accident and you want to see where the trouble-causing car is now, or where the car was in the past 3 days, we can use this search engine to search it. Of course, this only can be used by government, not by average users like us. Or optimize the traffic capacities based on optimizing, for example, traffic light scheduling. Or mind the patterns. I will show you examples later. And then we can do something more, is to predict the future. Of course, it's hard to predict which car is going to which direction. That's hard, but it's possible to predict the traffic flows after 10 minutes or 20 minutes, right? And even we can do a longer-term prediction. I often use this example, though it's not a real example. For example, in a city tomorrow, suppose there will be a heavy rain, and there are also a few big events. So you can imagine that there are a lot of people are going to gather in some places. Given this bad weather condition, you can estimate the possibility of congestion and the possibility of accident, right? Maybe will increase a lot. So you can do something beforehand to mitigate this kind of accident. Or you can even do something, we call it intervention, to prevent this from happening. Do some traffic control or give advices to people who is going to travel around that area, something like that. So all this, we call it a city brain. Right now it's more focused on traffic and a little bit of security part. So let's see a little bit more details of each steps. First, cognition. There are three requirements of cognition here compared with existing approaches. The first is that comprehensive. That means we want to know as many as possible things that are happening on the road, not only in traffic violations, not only in license plate numbers, but all the moving object, non-moving object on the road, outside the road, and what's happening on the road. And let me show you a few examples here. This is the basic thing, is the object and object attribute detection and recognition to locate and recognize targets like vehicles, pedestrians, cyclists, and also attribute of those things, including license plate numbers. We need to do it very fast and very accurate. And this is the one approach we used before. It's simple, but works pretty well. There are three differences compared to existing approaches. First, we turn it into multi-task problems, so they can enforce the network to converge to a better stage. And secondly, we have deconvolution layers to make the network work well, both for large and small objects. And thirdly, we have a voting scheme as a post-processing step to make sure we have very tight, very accurate bounding box. And based on these technologies, we have won the first places since May of 2007 for car detection in KITI benchmark, and also pedestrian detection, the first place since this January, and surpassed the second place by 2 points. And of course, license plate recognition is still one of the most important attributes of the object we want to detect. Actually, for good quality license plate, this is almost already resolved. But many license plate is not clear, or you cannot get sufficient number of training data because those, for example, the second one on the top, this kind of license plate in China, the number is small. It's hard for us to connect enough training data. So we use again to generate unlimited number of this kind of license plate. Because the license plate, the characters we know which kind of characters can be used in license plate. We can fake license plate and then transfer the styles of existing real license plate to this to this faked license plate. So this is we call it sterilized autoencoder again. And based on that, we can generate faked license plate. It looks real. There are two approaches. One is based on character level synthesis, and the other is patch level or the plate level, the whole plate level. You can see on the right, especially you can see the looks really like real license plate. And with this training data we generated, we have got 18% increase in recognition accuracy. Another difficult thing is to recognize what's happening on the road, like traffic violence, like accident. It's this temporal event, right? And there are many kind of this kind of event, but the training data that we can get is very limited. So, and also the difference between different kind of event are large. So it's hard to build classifiers to classify them directly. So the approach we are using here is to treat it as an anomaly detection thing. So all the normal videos, we have a large number of that. We model these normal videos. And then when an abnormal video clip was sent in, the response will be very high. That is the reconstruction error, basically. So this is a spatial temporal autoencoder-based approach, and the difference between difference here is that we have two branches in the decoder stage, and one is for reconstruction. This is a reconstruction branch. This is a very typical one, and we also have a new one. We call it a prediction branch. Prediction branch, we want to predict the movement of the object we care. So this branch actually enforces the network to take motions into account. So this, with this, we got a much better result for event detection. This shows you some examples like collisions, like motorcycle enters highway, which is not allowed in China, and illegal parking, and so on. So this is comprehensiveness. For completeness and real-time requirement, this is more about the efficiency of the algorithms as well as the entire system. So this is also very important for the whole system, because this means how much money you need to realize the system. And we don't have too much time talking about this. I only show you that this is based on cloud computing platform. More specifically is a stream computing platform. We make the stream computing platform work well for data-intensive tasks and computation-intensive tasks, like the video processing pipeline we are working on. And now let's talk about a little bit on decision and optimization. Decision, the first thing is that this is a screen recording of the real system running now in Hangzhou. So we can detect accident or other event instantly, and the traffic policemen are taking actions once they see this alert. And there are more examples here. Many traffic are caused by accident. So if we can find the accidents earlier, then people will start call the police. That will give us better chance to release the congestion, right? And another thing is that when the accident is a severe accident, there may be no people will report these instantly. If we can find this kind of instance earlier, maybe several minutes earlier, then people call the police, you will save people's life. This is very important for us. And if we count the number of accident or other event alertings for a period of time, we can find some patterns. And after rerunning this system for a few months, we found that there are 6 places that trigger a lot of alert. And then people will look into it to solve it offline. And the traffic light optimization, as we mentioned, that we know the cars, the people, so we know the traffic flows clearly, more accurately than GPS information than the coil data. So we can do a better job for traffic light optimization. Now let's talk about search and mining. We put everything we detect into a search engine. Looks like an image search engine, but here we care more about the object we find on the street. So there are two challenges here. The first challenge is the scalability. If you want to handle a huge number of data, it's not this slide. I removed it because we don't have enough time. This actually is the image indexing problem or high-dimensional feature indexing problem. This is a well-studied problem, actually. And the second thing is the representation learning. This is more computer vision challenge here. There are two categories of approaches here we can use. One is based on recognition. Use recognition tasks to enforce the network to converge, to be able to represent, to get a good representation of the object. Or we can use the re-identification tasks to something like triplet loss or pairwise loss to enforce the network to converge to somewhere we want. Or we can combine all this together into one network. For the second type of second categories, three kind of features we can use. Global label, this is a very typical one, and then part-based label and key point label. Let me explain a little bit about on the part-based label and key point label. So typically we use global label features for re-identification. Here we create a new structure that use the correlation loss in lower level feature map, so we can find the correspondence between patches, which will give us a much better result when we compare, we will identify the object. We can get a better feature from this network. And for other tasks like car identification, many cars are the same make, model, and color, right? And this is not easy for us to identify the right car. So here I use a network to learn features and key points, discriminative key points at the same time automatically, so we can get more discriminative features to differentiate these kind of similar cars or cars with the same make, model, and color. And on the bottom, you show some examples. We found some subtle differences between the cars. And based on this technology, we have achieved a top one accuracy of 96.17 in the well-known market 1501 dataset. This is a people re-ID dataset. And this is the best result as we know. And it is better than human beings' ability. Humans' ability is 94%. Okay, here are some examples for car search, car identification. For the second row, you can see the red box means the wrong ones. Actually, the second row, the rightmost three ones are the same in terms of make, model, and color, but they are not the same car as the query car because you can see there are very small differences there. And our technology can discover these subtle differences. So we ranked it lower than the real exact match. And for people identification, this actually is much more difficult because most cameras we have now cannot, see faces clearly. We have to use the, appearance, the figure, the features, the clothes, the color, the hair, and many things to identify people. This is much more difficult. We made more mistakes here. Now, prediction. As we mentioned that we are not able to predict which people is going to do what, but we can predict the traffic flow. Future flows, traffic flows are determined result of current flows of the intercity or a big neighborhood, right? Though this, of course, this can be affected by other things, and this can, like weathers, like accident, but this can also be considered in your framework. The basic idea here is that we model the traffic flow of a certain time frame as a graph, which is simulate the road network. And the task here is to mine the patterns between the graphs, between the traffic flows. For example, we have the traffic flows of time t and t-1 and t-2 and so on, and we mine the pattern, so we are able to predict the traffic flow, the graph of time t+1. Right? This is the basic idea here. Okay, let me summarize. This is the city brain we're now working on. Mostly you are focused on traffic, city management, and a little bit on security things. So with this, we call this city has a brain. So you can see the difference between city brain and the smart city. Now let me summarize what makes the city brain unique. There are three things. First, we are using AI and computing power to get irreplaceable values from big city data. This is the core of city brain. Secondly, actually we are doing things that human beings are not able to do because of the complexity of the problem, because of the data, and also the volume of the data. Right? And the third one is our goal. City brain hopefully will become a basic city facility like water and power, hopefully. So we have seen this slide before because deep learning computing power that enable us to do city brain because the complexity of the problems, the values that we can get from those data as well as the size of the data. So I believe that city brain as a platform can also hasten, incubate, and solidify the development of existing and new AI technologies as a platform. Thank you.